Hey everyone, this is the second video in a two-part series where we're looking at the relationship between acid strength or base strength and the chemical structure of that acid or base. So after we're done with this video, we ought to be able to predict the strength of acids or bases based upon their structures, and using that information we should be able to rank acids and bases in the order of their strength. In the first video, we talked about how we could look at the strength, or we could predict the strength of an acid based upon the stability of its conjugate base. Okay, so the strength here is related to the stability of the conjugate base. A more stable conjugate base comes from a stronger acid. An unstable conjugate base comes from a weak acid. We looked at two different things that can affect the stability of that conjugate base in the first video. Both of them we referred to as element effects. So in these cases, the atom in the conjugate base that holds that minus charge is different. It has a different element. And so we looked at the size of that element and the electronegativity of that element. So now in this video we're going to look at three more effects. In each of these cases, the electrons in the conjugate base are going to be on the same element. So these are really non-element effects. Let's look at an example here. Here are three potential acids. Notice that all they have is carbons and hydrogens. They're all hydrocarbons. Each of these belongs to a different functional group. The first one this is ethane. We would call this an alkane. Ethene is the middle one. This is called an alkene. Has a double bond. And the last one is acetylene, and this is a molecule that's called an alkyne. All right, so what do you think it is about these three structures which would influence their acidity? The obvious difference has to do with the bonding, right? So notice that in the alkane, we have all single bonds. In the alkene, we have a double bond. And in the alkyne, we have a triple bond. Okay, when we change the level of bonding, what else changes for those atoms? Well, the other thing that changes is the hybridization of the carbons. Right, so if we have an alkane here, this carbon, or both carbons, would be sp3 hybridized, right, because there has to be 4 zones of electron density around that carbon. What about the alkene? It has 1 pi bond, so this is sp2 hybridized. The alkyne has 2 zones of electron density, and so this is sp hybridized. So the hybridization of those carbons also changes. So we did learn something in Chapter 1 that had to do with bond strength and hybridization. Right? So let's look at carbon-hydrogen bond strength. Okay, do you remember from that chapter which has a stronger carbon-hydrogen bond? The hydrogen attached to the sp3 or the hydrogen attached to the sp? Okay, so in fact, the carbon-hydrogen bonds get stronger as we go from left to right. All right, so what do you think? How would that affect acidity? So for me, if I was just thinking about this, I might think that therefore, if the bond on the alkyne is stronger, that would make it harder to break, and I would suggest then that this would be stronger acids as we go to the left. Does that make sense? All right, so let's take a look at the pKa values and see if this prediction holds true. All right, so the pKa, we've seen it a couple of times, for an alkane is about 50. All right, super high. Okay, for the alkene, does it go even higher? No, the pKa of the alkene is about 44. For the alkyne is 25. So does this prediction that we just made hold true? No, this doesn't work. It is true that the CH bonds strength increases going to the right, but acidity isn't directly corresponding to the strength of that bond. So that might be surprising. I guess maybe I misled you here. So what else should we consider then? Okay, so let's go back to what we were doing before I led you off on that goose chase. What do we consider when we are thinking about acid strength? Well, we look at the stability of the conjugate base. So let's draw out each conjugate base. All right, so when we draw the conjugate base, remember we just remove a proton. That leaves a pair of electrons on the carbon, and so that's going to have a minus charge. So this is the conjugate base of ethane. Okay, here would be the conjugate base of ethene. And for acetylene, which is also called ethyne, here's the conjugate base. Okay, so these are the conjugate bases. All right, so can we say anything about the stability of those different conjugate bases? Well, it's probably not obvious here. So the way that this works is that as we increase the percentage of S characters, as this increases, the energy of the orbital goes down because an s orbital is lower in energy than the p orbital. So as the percentage of s goes up, the energy of the orbital goes down. This is of the hybridized orbital. Okay, so an sp, right? sp is 50% s, 50% p, right? sp3 is 25% s, 75% p. All right, so that means that the sp orbital is lower in energy. Okay, so if we put electrons into that orbital, they will be at a lower energy, and that makes that anion more stable. Okay, so that makes this anion more stable. Okay, so let's write it out down here. So we're going to be increasing stability of the conjugate base just write x minus for the conjugate base gets more stable going to the right. That means that we also get stronger acid that goes to the right. Okay, so this way is also going to stronger acid. Okay, so I think the moral to this story is that we want to stick with our strategy that we've learned, is that when we're considering acid strength, we look at the stability of the conjugate base. Let's look at these two acids. So in each of these cases, the first thing we need to do is to identify the most acidic proton on each of those molecules. So each of these molecules have multiple hydrogens, multiple protons, so how do we know which one is the most acidic? Well, it boils down to what we learned before, right? So if we have a hydrogen on a carbon, then that's not going to be a very acidic proton usually, but a hydrogen on an oxygen is usually going to be much more acidic because that oxygen is more electronegative than carbon. So the OH there and the OH over here are going to be the acidic protons. So like we did before, let's go ahead and write out the conjugate bases. Let's not get distracted this time. Okay, so we'll just remove that proton on the oxygen. This oxygen will have 3 non-bonding pairs of electrons and a minus charge. Let's do the same thing for this molecule over here. So minus here, this also has 2 non-bonding electrons over there. And this molecule is ethanol. And this molecule over here is acetic acid. You know where acetic acid is found? So acetic acid is one of the main, is the acidic component in vinegar. All right, so let's compare these two conjugate bases and see if we can decide which one would be more stable. All right, so I would say that this one over here, right, should be more stable. Why is that? The reason is because this molecule, acetic acid, the conjugate base, has non-bonding electrons on an atom next to a pi bond, right? So we can move these electrons this way and these electrons over here, and we can draw out a resonance structure. All right, so we saw this before. So from this resonance shows us that this minus charge is actually spread between the two oxygens. All right, so we see here that we have resonance. And so we're spreading the charge out, and this makes the anion more stable. Okay, so that means that acetic acid should be the stronger acid, has a pK of 4.8. Ethanol has a pKa of about 16. All right, so resonance can stabilize the anion, and remember, the more stable conjugate base comes from the stronger acid. So this effect is for resonance. All right, let's look at one effect here. So let's look at these 4 acids. Notice that they all have the same functional group here. Okay, so in each case, this is called a carboxylic acid. All right, this one over here is acetic acid. We just saw it on the last slide. Okay, and the rest differ from acetic acid in the presence of a halogen. So a hydrogen of acetic acid here is being replaced, in this case with chlorine, in this case with fluorine, and over here we've replaced all of the hydrogens in acetic acid with fluorines. Okay, So let's consider the conjugate bases again and consider what might stabilize those. So let's draw out each of the conjugate bases. All right, fluorine. And this one would be trifluoro. Okay, conjugate bases. So which of these would be more stable? Okay, well, we're not sure. Let's go back to writing out the pKa values. That'll tell us which one's more stable. Well, it'll tell us which acid is stronger, and that strongest acid gives us a more stable conjugate base. So acetic acid, we already saw, so these are going to be the pKa values. It was 4.8. What do you think about chloroacetic acid? Is it going to go down, or is it going to go up? Okay, in fact, it goes down to 2.8. All right, so chloroacetic acid is a stronger acid than acetic acid. Fluorine goes down a little bit more, 2.66. And if we have trifluoroacetic acid, it goes down to 0.2. Okay, so we are getting to stronger acids going this way. So that means that as we go across the conjugate bases, they're getting more stable going to the right. So why is that? What are the halogens doing here to make the anions more stable? All right, well, we know that those anions are more electronegative, so they are going to pull electron density towards them, right, from the carbon. It's going to pull electron density from the carbon. That carbon is going to end up short of electron density, so it's going to pull electron density from the next carbon. It's going to pull electron density from the oxygen. Okay, so in the end, that oxygen is going to have a reduced, or both oxygens in this case, are going to have reduced electron density, and we're going to end up with a small amount of electron density shared with each of these fluorines as well. And remember, the more we spread out the charge, the more stable the anion becomes. Okay, so this pulling of electron density through sigma bonds is called an inductive effect. Okay, so we could call this sharing electrons through sigma bonds, okay, through single bonds. Resonance, if we want to make a comparison, is sharing electron density through pi bonds. Okay, so the amount of inductive effect increases as this electronegative atom, like chlorine or fluorine, becomes more electronegative, right? The effect becomes stronger. If we have more of those electronegative atoms, like in trifluoroacetic acid, it becomes even stronger. Okay, so we're going to say that the inductive effect is stronger with more electronegative atoms and with more electronegative atoms, and if they're close. So if those halogens are moved more bonds away from where the anion is, the inductive effect will also be reduced. Okay? Let's look at some common acids and see if we can pick out the trends that we've been talking about already. Okay, so here on the left, we're getting more acidic going up. So we see hydrochloric acid on the top. We know it's very strong. So let's look at some of the trends. So if we look at an electronegativity trend, we could be going from methane to ammonia to water, right? These are differences in electronegativity. Right? If we wanted to go in hybridization, we could go from methane to ethene to ethine. So this is hybridization. Okay, we don't really have, well, we also have another one we could put in here. If we went from here to here, this would be resonance. And if we compare even water to chlorine, we're also kind of looking at size. Okay, so we see all the trends we talked about. So if we're increasing in acidity of the acids going up this way, if we look at their conjugate bases over here, notice that basicity goes in the opposite direction. So the weakest acid down here at the bottom gives us the strongest base, right? And the strongest acid gives us the weakest base. So how do we remember these? To do that is to break the different types of acids up into some different ranges and some different category ranges. Okay, so here's some common ones right here. So let's just break these up like this. We'll be adding to this table as we learn more and more functional groups. Okay, so notice on the left, pKa less than 0, so these are the most acidic compounds. Each one of these has an oxygen with an H on it and a plus charge on the oxygen. Okay, includes hydronium ion, protonated alcohol. Notice this one is actually a protonated carboxylic acid. So whenever you see molecules that have an oxygen, a protonated oxygen where the oxygen has a plus charge, these are going to have pKa's down below 0. They're going to be very strong acids. Okay, so that's below 0. Another common category around pKa of 5 are the carboxylic acids. Right? We know that can go even lower if we start to add electronegative atoms to that. Here, let me just tell you one thing that maybe we haven't seen yet. This R group that they're showing here, this is just for some kind of generic organic. Okay, so it doesn't really matter what that is. So it could be 2 or 3 carbons, it could be a ring, but it doesn't really affect the functional group. So the next category up that we're looking at are the protonated amines. So these are the ammonium ions. They have pKa's around 10. Then we have normal OHs, like water or alcohols, pKa around 15. And then we have the actual amines, so the nitrogen with a hydrogen on it, and their pKa is in the 35 to 40 range. Okay, so if we know these kind of general ranges, this will let us really go a long ways. And we'll see these over and over again. It'll help us to remember. So let's do a couple of examples here. So what we want to do in this example is to rank these acids in order of increasing pKa. So we're going to go from the low pKa to the high pKa, or the more acidic to the less acidic. All right, so in this one, let's go ahead and do what we've been doing. Let's draw the conjugate bases. Okay, that's an alcohol. This is a carboxylic acid losing its proton. This is a special kind of alcohol because it has this benzene type ring. We'll figure out why it's special in a minute. And here's hydrobromic acid with Br minus. All right, so how do we approach this? We want to rank the acids. So we want to find the more stable conjugate bases. So the first thing that we usually look for is size. All right? So if one of these minus charges is on an atom that's below the second row in the periodic table, that's going to be the most stable, and it's going to come from the strongest acid. Okay, so bromine is the lowest in the periodic table here, so this is going to be going to come from the strongest acid. Okay, because this is has to do with the size. Okay, then notice that these three all have oxygen. All right, so they're all the same atom. So what do we look for next? All right, we don't have any more electronegative atoms, so there's no inductive effect. But we do have some situations where we have, like the carboxylic acid, where we have non-bonding electrons on this oxygen, which is next to the pi bond, and so this can have resonance. Okay, what about the one on the left? Does it have resonance? No, this has no resonance over here. Okay, the electrons on this oxygen are going to be localized. They can't be shared anywhere. Okay, so this is going to be the least stable. Okay, so this is going to actually be number 4. All right, so what about this one that I haven't commented on yet? Okay, this one, let's draw out its non-bonding electrons. 2, what do you think? Can that molecule have resonance? Well, in fact, it can. Look at, there's non-bonding electrons on the oxygen, and that oxygen is connected to a pi bond. So these electrons can go down here, and these can go over to here. Let's draw out our resonance structure. Okay, we push these electrons over here. Okay, so we have this other resonance structure. Okay, so we have 2 that have resonance. So how do we figure out which one is more stable? Well, the thing that plays a role in here is notice that for the carboxylic acid, we're sharing the electron density between 2 oxygens, so 2 more electronegative atoms, all right? In the one on the right, we're sharing the electron density between an oxygen and a carbon, and that's not quite as good, all right? So this is going to be the second most acidic, and this is going to be the third most acidic. Let's draw out what the pKa's up here would be. So the pKa of alcohols is about 16. Right? Carboxylic acids, we said were about 5. This is phenol. It wasn't shown. Those are about 10, though. And HBr is minus 9, I believe. All right? So we looked at size, and then we looked for electronegativity, but we did find resonance. And that was the second thing we played into this. All right. Okay, let's rank these. Let's try to do these without drawing out the conjugate bases this time. Okay, so what do we have? We have hydrogen on a nitrogen. The other 3 have hydrogens on oxygen. Okay, so this is going to be 4. All right, because that atom is less electronegative. All right, we have hydronium ion. We know that the pKa here is less than 0, so that's very acidic. What's the structure on the right? Okay, this is actually sulfuric acid. So what happens when we put sulfuric acid in water? Right, it completely dissociates to give us hydronium ion. All right, so it doesn't go back the other way very easily, so sulfuric acid is actually a stronger acid than hydronium ion, and that's much stronger than the alcohol, right? Because this has a pKa of around 16, this has a pKa of around 38. All right, so why don't you try this next one on your own? So just to summarize, in the last two videos we have looked at relationships between acidity and structure. We observed how strong acids yield stable conjugate bases, right here. Weak acids give us unstable conjugate bases. We looked at these 5 things that can influence the stability of the conjugate base. We looked at the size of that atom, the electronegativity of that atom. We looked at how hybridization can change the acidity. We looked at the presence of resonance and inductive effects. So I broke these into 2 videos because this is very important content, because you're going to be looking at acids and bases throughout all of your chemistry, but especially through the rest of organic chemistry. So the more comfortable you are with acid-base chemistry, the better off you're going to be.